Welcome to this PyTorch beginners video. Torch is a popular deep learning framework that has gained immense popularity in the field of artificial intelligence and machine learning. Torch is designed to be flexible and easy to use, making it a great source for both researchers and practitioners. Torch has an intuitive and easy to use interface, making it a great choice for beginners. Torch is designed to be flexible and adaptable, allowing users to easily experiment with new models and ideas. And it also supports GPU acceleration, allowing users to train complex models faster than on a CPU. And it also has a wide range of pre-built modules and functions, making it easy to build complex models without having to write everything from scratch. Also, Torch has a large and active community which provides excellent documentation, tutorials, and support, which is called PyTorch forums. And all in all, PyTorch is a powerful and versatile deep learning framework that provides users with tools that they need to build, train, and deploy cutting-edge machine learning models. With its easy-to-use interface, flexible dynamic computation graph, GPU acceleration, pre-built modules, and active community, PyTorch has become a popular choice for researchers and practitioners alike. Whether you are just getting started with deep learning or you are an expert, PyTorch is definitely worth considering for your next project. Now we'll look at how we can install PyTorch. So now we'll go to pytorch.org and scroll down, and we'll get the install PyTorch here. From now, what we have to do is a combination of this. So select your OS, select your version of PyTorch, and what kind of package are you using. If you're using a Conda environment, you can use for a Conda installation, or you can use a pip installation. And if you're using the language and GPU and CUDA. Also one thing, if you're using a Mac, CUDA support would not be enabled as of now. So if you're using Windows or Linux, you can go ahead and install any CUDA version, which actually allows you to train models in or use GPU support. And what you have to do is select your combination of the configurations, and you just have to paste in the command that you get in here into your terminal, and Torch will be installed. So now we'll look at some of the basic tensor operations on PyTorch. For that, first we'll import PyTorch. We'll also import NumPy because we are going to see how we can convert NumPy arrays into tensors and tensors into NumPy arrays. So the very first tensor that we are going to look at is an empty tensor. So let's just say x equals to torch dot empty of, we have to pass in a size and print x, and we see this is an empty tensor, so the values are not initialized. So this is the place that we have to give the shape. So the shape can be even 1 dimension, 2 dimension, 3 dimension, or even higher dimensions. So this is just a 1-dimensional empty tensor. So we can change the shape just like this. So now this is a 3x5 matrix, or I would say 3x5 tensor, PyTorch tensor. Let's just say this as empty and empty. This is an empty tensor. So now we look at how we can make a random tensor. So random equals to torch dot rand of, let's say we have a 1-dimensional tensor with 2 elements in it. So let's connect with this. Or or we can change the shape around to cross 2 or even to cross 2. This is a 3-dimensional tensor, and so on and so forth. But the elements are random, and it's taken from a distribution from 0 to 1. And we can make, like we would make a 0 array or array of ones in NumPy, we can also do that in Torch. So we just have to do torch dot zeros, and we get a person a shape. Let's just say 2, 3. So this is zeros, and we got zeros. So we got a 0 tensor with all the elements as 0 of the shape 2, 3, and it's a 2-dimensional tensor. So the same way, if we want like a tensor of ones, torch dot ones equals to torch dot ones of let's say the same shape, or even we can go into a higher dimensional space, it doesn't really matter. So it's just going to be ones. Okay, so that's it. Now if you want to check the data type, so all of the tensors that we have actually made here, empty of random or ones or zeros, we can look at what are the data types of the element, and I can do ones dot d type, and it's going to show me d type, and it's going to show me the data type. Or we can also look at it starts dot float 32, and we can also look at its shape. This is its shape, and this is another method, and we discussed now 2 methods. So one is shape, other one is d type. And now we look at how we can, okay, I'll document this in here, ones dot d type, and returns the data type, and this returns the shape of the tensor. Now we look at how we can make a tensor from a Python array. Let's just define an array. I'm going to write an array equals to 1, 2, 4, 6, 5, and we are going to change this into a torch tensor. So this is going to be torch dot tensor, and you can pass in the array, and t array t tensor equals to tensor is going to be a torch tensor of the same array that we defined. So if this is a nested array, then you're going to get a multi-dimensional torch tensor. So one more thing that I have to specify in here is if I check the torch tensor t-tensor dot d type, I'm going to see int 64. So if I want to change the d type, what I can do is I have an argument in tensor. So d type equals to torch dot int 32 for example. So I changed it into int 32 from int 64. So this way we can specify what sort of data type that we want the elements to take. And now we look at some of the basic operations that we can do with tensors. For that, I'm going to define x equals to torch dot rand 2, 2, and y equals to torch dot rand of 2, 2, and let's just say I want to perform addition. This is going to be an element-wise addition. So if I want to do x plus y, what I have to do is just let's just say z equals to x plus y, and you can print z, and this is just an element-wise addition operation happen. So there's also an alternative for this one, and alternative is dot add of x comma y, and both of these things are going to give you the same thing. And now we look at how can we do subtraction. It's an element-wise subtraction. So z, let's say x minus y, and we can print z, and it's going to give you element-wise subtraction operation done, and the tensors are done. Also, we have dot sum of x comma y. Yes. And now we'll do multiplication and division also. So multiplication is done through, you can call x star y. It's going to give you that element-wise multiplied. We'll print it out, and also dot mul of x comma y is going to return with that. So I'm going to explain division also. Division, div, and x by y. X comma y. Okay, so these are the very basic operations, tensor operations that we can do with tensors. So it doesn't really matter what kind of tensors that you have, you can always do this kind of operations with tensors. Given the mathematical norms has to be followed, but this is a element-wise operation, so the tensor shape has to be the same. Now we'll look at tensor slicing. For that, let's just make a tensor. Tensor equals to dot rand of just say a 3, 5, 4, and this is our tensor, and so this is our tensor. So what if we want like so point is, this is a slicing operation that I'm going to demonstrate. So you can slice the tensor. This is the entire tensor, but you can slice it like usually how we would slice something in NumPy. Let's just say 1, 1. This is going to give you everything from the first dimension, and the second element from the first dimension, and the second element from the third dimension as well. So if you want everything, you can do this, or if you want some certain values only, you can it's some certain elements you can do this, and so on and so forth. So that's just about slicing. But one particular thing, tensor of, let's just say I want to slice it 1, 2, 3, and this is going to be a single elemented tensor. So whenever we have a tensor with only one single element in it, what we can, PyTorch has some sort of functionality to retrieve only the element from it. So let's just say A equals to tensor of this particular element, or I may say element equals to, and print out element, and we'll see it's just one element, and we can do dot item, and we can get the element only. So that's what you're seeing here. So dot item method is very useful when you have a tensor of just one element, and if you want to retrieve that element. So the next function we'll go to is something similar to a reshape on NumPy. So if you want to reshape a tensor, let's just say our original tensor that we define now, which is a big one, so we can look at its shape, and it's 3, 5, 4, and if we want, we can to look like tensor dot view -1 comma 5, and it's going to look like exactly that. So -1 is specified for a non-dimension. So I want the so essentially what I'm doing is I'm converting that tensor of 3 dimension into a tensor of 2 dimensions, and the second dimension I want I specified I want 5 elements, and the first dimension I'm basically saying by giving a -1 is whatever the dimension we have once we set the second dimension to p5. So that's it. Or you are actually free to do any sort of tensor dot view. You can do like 5 previously it was like 3 5 4. You can do it like 5 3 4 or any of that sort. So the reshaping is always possible, but you have to follow that logic of it. So the size of it and the number of elements on it, and logically it has some sort of a connection. So you cannot always reshape it into very higher order because the elements would not just have that many elements. So just follow the logic, and you will be able to do this kind of things. Now we look at how we can convert back and forth from NumPy. So for that I will define okay, we can define the tensor that we have now. So this is a high dimension tensor. So dot NumPy is going to be np array equals to, so np array, and once we have done dot NumPy, it's going to convert that into a NumPy array. So the tensor will be converted into a NumPy array. So now we can say you can see this is a NumPy array. So one thing is, in a CPU both of those things maintain the same memory. So if you are computing on CPU, not on GPU, so the same both of those, one of the tensor and the array is going to share the same memory location. So if you change one of them, the other one is going to automatically change. So you may have to be really careful for that. So we can do now our NP array is a NumPy array. So if you want to convert that into this is NumPy array, and if you want that into back into a torch.tensor, what we can do is torch.from NumPy of NP array, and save this into some other variable, maybe tensor 2 and we can print tensor 2, and you can see again tensor. So these two functions are what we use to change back and forth between NumPy and torch tensor. So now if you want to use CUDA, if you want to check if CUDA is enabled or not, or does your system have CUDA support or not, you can actually have a command in torch.CUDA is available, and this is going to give you if CUDA is enabled or not, which is a GPU support in Torch. In my case, it's false. So once you enable it, you're going to get it as true. So what you can actually do is, if you have a CUDA enabled you can do this kind of a loop. If CUDA enabled, you can change your device. Torch.device of and a string, pass in a string in this one, and now your device is CUDA. So what you can do is you can specify. So now if you want to make a tensor in a GPU, what you can do is tensor equals to dot tensor, and you can pass in your values, or you can do any kind of initialize any kind of tensor, and you can specify maybe a d type, torch.int or torch.int, let's just say torch.float 32. And once you have done that, you can specify the device here itself. Device equals to now our device. So now our tensor is going to be inside the device that we specify. So in this case, this block will only execute if CUDA is available. So then the tensor is going to be inside a GPU. Or one more thing that we can do is here we have initialized the tensor and pass it into the CUDA device in one line. So you can also choose to define the device first and make a tensor of let's just say a random tensor, tensor2 equals to, and then this tensor2 can be passed into .2 device. So this is also going to be of the same operation. Tensor2 is equal to tensor2 dot to device. So both of these things are of the same operation. One you are executing while you are actually making the tensor. The other one is after you made the tensor. So one more thing that we can discuss here is once we when we make a tensor in or out of the CUDA, one more optionality that PyTorch gives is the required grad. So once you make a tensor, or let's just say torch dot, we'll use a different method to make a tensor. So we'll make a torch dot rand of 3,3, and we'll ask here requires grad equals to true. So this enables this tensor to be part of a gradient computation loop, which means once we have computed something, once we have computed maybe a quantity using this tensor, then we can always come back and compute the gradient of that quantity with respect to the elements of this tensor. So that functionality will only be available if our tensor is initialized with required grad equals to true. So that is this functionality for optimization, backpropagation, and that kind of usually in machine learning and deep learning. One more thing that we have to look at is PyTorch documentation, which is really good. So from what I've discussed in the tensor tutorial, what this is going to be an extension of that. So what are the different, there are like plenty of other different functions that we can define on top of a tensor, plenty of different operations that we can do with tensors as well. So what I want you to do is come to pytorch.org, the docs, and you're going to see the documentation of PyTorch, and a couple of submodules that you're gonna that you should be looking at are, one is Torch. So Torch has a lot of functions in it. So let's just say max, min, argmax functions, softmax function, and different that kind of functions that we would generally use in PyTorch. Also concatenation functions and reshaping functions, and a lot of other functions are defined. Plenty of other functions are actually defined on Torch. So this is something that you want to keep an eye on. And this is just an extension of what we have discussed in it. There are a lot of methods in here, and you can go through each of them. The documentation is wonderful, and it's got examples as well. And many of those functions will not be actually necessary for you to get started with doing machine learning or anything. But it's always good to understand and go through the documentation and find what sort of options that we have available at hand. And the other one would be computational, very much computational, the core of computation, and the most important thing would be torch.nn. So torch.nn's got different containers, convolution layers, pooling layers, padding layers, activation functions, and normalization layers. So these are all the things that we would use once we are doing a more deep learning specific problems like a computer vision problem or an NLP problem or things like that. So we got, let's just look at one of the examples, and I will show you, let's just say we want to look at a recurrent layer. Let's just say nn.rnn, and it's got the documentation, and it's got what is this RNN, and what is the output look like in the RNN, and things like that. There are like mathematical equations and different arguments and parameters specified and detailed description. And we got examples as well in here how to use it. So it's going to be really easy for you to extend the knowledge that you gain now. And this is going to be really hardcore computational because it's going to be torch.nn is going to be pretty much what we are going to use when we are creating a model. So the layers are very important. So the other one that I want, so we got also torch.nn.functional, which are the functional versions of all the other classes that we have in torch.nn. So let's, for example, a convolutional layer is going to be defined as a class in torch.nn, but in torch.nn.functional we got a functional alternative of different classes, all of the classes. So you can check out and you can use it in a slightly different way, but it's going to be really effective once you have something to compute. And one more important thing I would say is torch.optim. So torch.optim's got a wide variety of optimization functions, and we'll slightly look at them. So what I want you to do is look at them, and you may have heard of different optimization functions, and most of them you may have heard of could be defined in here. So I want you to go ahead and look at different optimization functions. Let's just say stochastic gradient descent, and you can have a look at it. If you know how it is working, and it's really going to be really simple to implement it on PyTorch. And let's just say a lot of atom optimization or digrad optimization and different algorithms are implemented in here. And also one more thing that is in here is torch.optim.lr scheduler, which is like a learning scheduler. So you're gonna see that one also in here, learning scheduler, learning rate scheduler.
So right now what we are going to look at is how does logistic regression work. So this is going to be a theory session. So before we go into the programming part of it, we'll try to implement it on PyTorch, and before that we'll look at how does it really work. So logistic regression, first thing, I'm going to write down a couple of points related to logistic regression here. So this is a classification model, and we make use of something called maximum likelihood estimate, and then I will make a loss function, and then we'll try to optimize something. Okay, let's just get into the session. So logistic regression is a classification model, so we can use it for classification purposes. So let's just look at the dummy table that I have in here. So I got some x and y. So x is representing the features and y is our labels. So what you want to create is nothing but a y dash, which would be predictions for y. So x can not only be like just one feature, it can also be like multiple features, many different features. It doesn't really have any sort of limitation when it comes to the number of features, I mean number of columns that it can take up. And so we'll now have a look at what maximum likelihood estimate is. So okay, so for any classification method, we would want our output, the network output, the output that the predictions that we are creating, which I am going to describe as y dash. So y dash is going to be our predictions. So this is our spreads, and y is our real value labels. So these are our labels. So what we would do is we want to develop a model that in theory would produce y dash equals to y, and even for the unknown values of y, we want our y dash to be equals to y, which is actually unknown, but we are trying to estimate it. This is a supervised learning technique. So we, throughout the training process, we'll have access to y, which is the real labels. So once we have y, what we can actually try to do is try to make predictions. So those predictions has to have certain characteristics. So if I formulate that characteristic, it would look like, what we're trying to do is a probability. We want the probability that y dash, what we produce, equals to y given, this is a condition probability, given the features x and the parameter that we use for that, which are the weights and biases of the network that we create. This to be equals to 1, or this at least should be very high. So in theory this has to be equals to 1. So 1, you might ask why 1, because the probability values for any probability, a definite probability value, would range from 0 to 1. This is an inclusive interval. Okay. X's are our features and theta are the parameters that we use to produce x. And essentially what sort of, so when we are creating a network, what we would do is this is a linear equation. So this is a linear model first of all. So when we create a model, what we do is we want a prediction y dash equals to theta dot product x plus theta naught. So in the equation I have omitted the theta naught part, but you can add the theta naught part. Actually this includes all the variables including theta naught also. So this theta includes the theta and the theta naught as well. So this parameter and this parameter. So these are the parameters of the model, and our y dash is going to look like this. And our y dash is actually completely depending on two of the parameters, theta and x. I mean theta naught and x. And when you look at training, what we would try to do in logistic regression is we would go through every sample y1. We'll try to predict the y1 for y1 dash for y1, and which has features x1. So y1 dash equals to y1 given x1 and theta. Theta are fixed parameters which you would actually change in iteration, which I will come to that part later. And so this is the probability that one of the predicted value is equal to the original label, and we would like this probability to be 1. And not only that, we would like all of the samples and all of the prediction for the samples that we have equals to its real label. So what we would want to actually maximize is the probability that y2 dash equals to y2 given x2 and the variable, the parameters theta, and we'll multiply this until our samples run out, till n, I would say. So this is going to be an equation like this, from I equals to 1 to n, n being the total number of samples. We will do this y of I dash equals to y of I given x of I and theta. So you want to maximize this the probability. This is actually a product, so you want to maximize this probability. So this is called the maximum likelihood estimate. And if you have an algorithm that can maximize this equation, then you're going to essentially end up producing all of the labels that are going to be close to what the real labels are. I mean, all of the predictions that are close to what the real labels are. So in actually optimization, so we need to optimize this equation essentially. But in optimization, people usually, it's just a convention. You don't actually have to follow it, but this is a convention the world follows. So what people does is, people doesn't really like to maximize this function, any function. So I'll specify maximize this. But people doesn't like maximizing things. We like minimizing things. So what we would do is we'll wrap a negative log of this equation. This function, what is a good thing about this function is this has a good convex shape, so which is really good when it comes to optimizing and finding the minimum of the function. So this is our loss function, or in Torch we will call this the cross entropy function. Entropy. And we'll try to minimize this thing. So when we are trying to minimize this thing, what essentially we are doing is we are maximizing this maximum likelihood estimate. So maximum likelihood estimate has some sort of a constraint on the predictions that we are making, that it has to have a high probability that it is equal to the real labels. So once we optimize this thing and once we find the so you might ask, the model parameters are theta and theta naught. So we have theta and theta naught. Once we optimize this thing, or we wouldn't optimize this thing, so essentially what we are going to do is this thing. We'll create a model in Torch, and Torch, what happens is whenever we create a model, we'll have certain layers. Let's just say first hidden layer, second hidden layer, and so on. So Torch randomly automatically assigns from some distribution some values for theta and theta naught that are taken from some sort of distribution, so which will be assigned. So the initial theta and theta naught will be assigned to all of the layers that we create in the model. So once we do that, what we need to do is make a blank prediction. This is actually the training loop. Okay, this looks like, I will erase these things. Oops. I'll write our model is of theta and theta naught. Then we feed in our x's. X, let's just say this is a vector, which means this has multiple features, also multiple samples in it. So you can expect the size to be like m cross n, where m will be the number of sample and n will be the number of features. And once we have this thing, what we will do is we'll pass in our x's. So once we have our x's, the model will try to compute the y dash, which is, as we have specified earlier, is going to be theta dot x plus theta naught. This is our y dash. Now if you look at our MLE and our loss function, this is our loss function. If you look at our loss function is actually a function of all of the parameters that we have now. So we'll feed this thing, and our real value, our real value is y, and the theta naught and x into the loss function. And what does loss do is that function will compute a loss. Let me denote this as the loss function. So this loss function is this cross entropy function. So this function is the loss function, and this loss is going to compute a value. Let's just say this as a value, loss, a value. And what we would want to compute is, if you are doing stochastic gradient descent or any other sort of gradient descent based algorithm for optimization. So until this point, this is the computation of loss. What comes now is called optimization. So what we'll try to optimize is this function. So this function, as I told, could be a convex function, but it in general would be a little more complicated than that. So what we want to compute is this value. So again, this value I'm going to call the loss or the value. Okay, I'll call it the value. What we want to do is find the partial derivative of the value. I don't usually call it the value, but I'm calling it the value. Theta also of value with respect to theta naught. So when I say theta and theta naught, they are vectors. So, or we don't denote it like theta and theta naught. Usually we would denote it as a theta vector. Okay, so if I denote this value as L, not the function L, let's just say this is a function L, this is a value L, okay, let me call this the loss. Essentially this thing would read, systematically written, would read del of loss with respect to del of theta, which can be very systematically be written as the gradient of theta loss. This is the del operator. So we want to calculate this thing. So once we calculate this thing, what we have in our hands is the gradient. So we want theta to undergo certain operation which is called theta equals to theta minus eta so this eta is our learning rate, LR, learning rate. So this is the sort of updation that we perform when we call loss dot backward and optimizer dot step. So this job is done by an optimizer in PyTorch. So usually we would call it something like SGD, stochastic gradient descent, or if you are doing batch wise, then it'd be a batch gradient descent, or you can have more sophisticated algorithms like Adam optimization or Adam W optimization and things like that. So those are the things that perform this kind of a step. So this step even could be complicated. So this is the basic stochastic gradient descent sort of a step that I'm explained in here, stochastic gradient descent. So if you don't know that, you have to look at how it is done. It is pretty much this is the thing that it does, but if you want a detailed understanding, just try to have a detailed understanding. So for facilitating these things, this sort of a gradient update. So once we have gradient update, what happens is, okay, I will explain some of that as well. So understand this is what the update that we are going to do. So why we are trying to do this update? It's because let's just say our negative log of maximum likelihood estimate is a convex function like this. So what I'm saying is, once we have our theta, once we have a loss, we look at its gradients. So if our gradient is decreasing, that means our theta has to be updated accordingly. So at this theta, when we calculate the slope is negative. So once we have a negative slope, what we have to do is go in the forward direction to get into the minimum theta. So once we have, let's just say the theta is in here initially. Once we calculate the slope, which is del L by del theta in every dimension. Here it's only one dimension. So if the slope is then positive, we have to update theta in the negative direction. So that's exactly what we are doing here, but there's a constant sort of weighted. That's the reason why we are giving the learning rate. So that's it. So in Torch, the first thing that we'll do is we'll write a criterion. So in this case, it's going to be logistic regression. For logistic regression, this is going to be maximum, cross entropy loss. And the second thing that we would do is we'll define an optimizer, and this is going to be SGD, just SGD, which stands for stochastic gradient descent. And the third thing would be we'll pass in the labels and our predictions into the criterion. This is going to give us the loss. This is a value. So once we have this loss, we'll call loss. We'll need to calculate the gradients with respect to loss. So calculate grads with respect to loss. This is done by loss dot backward in Torch. So these are torch methods that I'm referencing. So okay, later I will highlight it with something. Okay, but for now, and after, once we have found the gradients, we need to update the gradients, I mean update the weights with respect to, I mean depending on the gradient values, update weights and biases. And for this we'll call optimizer dot step. So these are the essential things that you need to know. So that's it. Let's just get into the coding part. We're going to look at how can we implement logistic regression in Torch. So first thing that we are going to need is a data. I got a data in here, which is wine quality dataset, and we try to implement a logistic regression model on that. So we try to pre-process it a little bit, and then we look at making how can we make a data loader, and then we look at how can we make build a model which is a logistic regression model using different layers on PyTorch, and then we'll try to implement a loss function and optimizer, and finally we will try to do a training loop. So these are, whatever I explained in here is majorly the sort of like steps that you have to follow for doing any sort of project on PyTorch. So you have to have a model and a data loader, which are two necessary things that you have to write if you are dealing with any sort of problems, or any sort of problems which you are going to implement in PyTorch. So let's just get started with this. I have already loaded the data here, and if you look at the data, not much of a pre-processing is required in this one, because everything is, as far as I can tell, is a numerical data type. And yes, that's it. So we'll try to do a data loader. We'll try to write a data loader from now. So what we have here is a lot of independent variables and one dependent variable, which is the quality here, which is what we are going to predict. So the quality is what we are going to predict, and using all of the other features in here. Let's just look at the quality. So quality's got like 1, 2, 3, 4, 5, 6 values, 6 unique values. I mean 6 unique outputs they are expecting us to produce. So this is a multi-class classification problem. The loss function that we are going to use is the cross entropy loss, which would expect us to produce outputs in 0, 1, 2, 3 and that range. So this has to be starting from 0, 1, 2, 3 and so on. So it cannot be any random integer. So we need to change this labels accordingly in 0, 1, 2, 3. So for that, what I'm going to do is I see that here we got starting from 3. So I need it to be starting from 0 and so on. So data of quality, this isn't actually an important step or anything. This is just, I'm just doing this because this is the way actually the cross entropy function takes any output or any labels when we are giving it with the output. So I have just changed the data quality, which is our target. So now it's nice and unique from 0 to 5. So now we will try to make a data loader. So data loader has to be beginning with importing torch. I'll import torch, and then I'll import one more thing, torch dot So these are the two things that I want to import right now, because constructing a data loader could seem complicated if you have not constructed one before. But this is actually really simple. So I'll start writing a class. A class would class that is going to take our data, our wine quality prediction data. I'm going to call this class dataset, and this class is going to take the original data, and it's going to do a couple of things. The first thing that we want to do is, the reason why we are writing the data loader is because we want our data to be delivered in batches. In deep learning specifically, usually the data sets are really huge, so you cannot deliver it in one batch at a go. So you just have to split it up into a batch size that you specify, which your memory can handle, and then you have to deliver. That's the reason why we are implementing this thing. So this is taking data. So once I'm done with it, I'll explain it. So I want this to be creating train X and train Y. So train X is going to be data of data dot. I'll drop all the drop only the predicting column, which is quality. Drop quality, and the access has to be specified equals to 1, and in place false, because I don't want it to be in place, because I'll also be using it the next line. And of course I don't want this to be in numpy array. So if I call this values, this is going to be a numpy array. I want this to be in torch because we are implementing it in torch. So this will be a torch.tensor now. And in torch framework, whenever we are training, we would want to make sure that the data types are really correct. And usually for all the independent variables, you need to have float 32, and train Y, the dependent variable has to be a torch.long data type, which is actually in 64. So torch.tensor data of quality and dot values, and then you can specify the type torch dot long, because the loss functions defined in torch expects this one, so otherwise we will not be able to train it. So I'll just mark it here. Torch dot long is for training, training. So if your dataset is going, if you are not using your dataset for training, or I mean the data loader for training, or if you want the data loader to be used for something else, or batching and doing some processing or something like that, you don't necessarily have to follow this this sort of like convention for the data type, and that's the reason why I'm specifying it. So the next function that I want to write is length function, which is a double underscore method, and this method would make this class understand what is the length of the data that we are fed in. So I want it to return len of our self dot train X or train Y, doesn't really matter, and train X and train Y is of the same length, and then define double underscore get item. So if you don't know what get item and length functions are, then I highly recommend you to understand this one, because these are the methods that we can actually implement in class, which would facilitate the class to certain operations that we can do on top once we have defined the class. So I highly recommend you to actually go through a couple of these render methods, and if you don't understand this, it is actually quite easy. So then what we want to do is return, I want to return a dictionary, and I want this to be access to be x. So x should be self dot train x of idx, and come on, I want y self dot train y idx. So these are the two things, and once you set it up, idx typo, sorry. So once we have defined this thing, we don't have any problem. Okay, so our data set. So this data set of data, and let me call this wine data. So this is our wine data. So if I look at length of wine data, so this is retaining 1600. So this is facilitated by the double underscore length method. And if we want like wine data of 3 is going to return, this is because of the get item method that we defined. So this class now have the ability to understand what is the total length of the data. Also it has the ability to get any of the rows that you specify the data to be. So this has this many qualities. So now what we want is, the reason why I imported torch.data loader is because data loader is something that can take this class and return data in batches that we specify. So if you want like data to be delivered in like a batch of 10, then it can do it. If you want it to be delivered in batch of hundreds, it can do it. And apart from that, it has also different functionalities like it can shuffle it, you can add a collate function and things like that. So it's really a nice thing to know. So this data loader will take now our data set, our wine data. So wine data has the sort of properties that we defined, and we want the batch size, let's just say batch size of 10, and shuffle equals to, you can set this true or false depending on what point are you in the process. If you already shuffled your data, then you don't have to do it, and if you haven't shuffled it, then you can try to shuffle it in here. So it really depends on how you are actually formulating it. So I would for now I'll give it shuffle equals to true in here. And once you have let's just say this is train loader equals to this thing, and train loader, if I look at the train loader, it is object. And what I'm going to do is I need to look at if everything is working fine. So I'm just essentially what I'm doing is I'm converting it to an iterator, and then I'm calling the next on it so that I can see the function, I can see the data that it is delivering. So as expected, I got a dictionary of 2 keys and 2 values. So X is delivering all the training examples that we want, and Y is delivering all the labels that we want. So of X is going to give you the X's only, or Y, Y is going to give you the Y's, the labels. So all of them are torch.tensors of the specified data type. So this is the data loader. So once we don't also one more point is that I just called iter and next method just because I just only wanted to do see if it is working or not. So in training, what we would do is like we can actually trade through this one. So train data for let's just say batch in train data print. If I print batch, then I'm going to break in here because there'll be a lot of batches, and yeah, train loader, I'm sorry. So function is train loader. So this is going to iterate and give our output dictionaries, iterate through the train loader. So this is what it is. So the next thing that we want is create a model. So our model is going to be a logistic regression model. So for this we already imported a couple of things, so I'm changing all the imports into one place so that it'd be easy for you to analyze it. Import torch.nn as nn. So now that we have done the data loader, we need to write a model. So our model is going to be class logistic regression. This has to take nn.module as its parent class. This is something that is different in PyTorch. So every class that we write has to take nn.module as its parent class. So then on we can implement the methods that are written in nn.module into our class also. What we can do is define init self and we need to have a couple of things in this class. So one is the input shape, which is nothing but the number of features that we have, and maybe a hidden state, hidden shape. So if you have a hidden unit in between, and the output shape. Output shape is nothing but the number of outputs that we want. So here we will write self dot, okay, we don't have to write that. So self dot layers equals to nn dot sequential. Here we will define nn dot linear input shape, comma hidden state, hidden shape, and here nn dot linear. So our network's got like two layers, nn dot hidden, oh sorry, hidden state shape, comma output shape, output shape. Now what we have to define is a forward function. So before defining a forward function, I will try to do a couple of other things. So one thing that we have to always do is make a class called config, and here we can actually have all the parameters that we want to be defined. So for instance, we have defined previously something called batch size, so which is for training. So we previously gave like batch size equals to 10. So what we can do is make a parameter train batch size and equals to you can set this into 10, and here what we can do is config dot train batch size, so that if you do want to change the parameters a little bit in case of you doing hyperparameter optimization or something like that, you don't have to go searching for where the parameters are. So if every parameters are defined in here, it'll be much easier to change things around. So now we'll go to our forward function. So the thing that we are trying to do in here is called a forward pass. A forward pass would do nothing but it'll just take the data that we are giving, and then it'll give it to the neural network that we have just defined, and it will just give you the output. and the outputs are going to be random numbers. Random numbers that doesn't have like a range or anything. It can be any number. So what we want to make is, in logistic regression, we want to make that into a proper probability value. So for anything to be a proper probability, it has to be in 0 to 1 range. So we have to change it using a softmax function. And we don't have to explicitly do that, but the cross entropy function that we will define, which will be the loss function that we are going to define, which will take care of that. But once we are given the output that we get from the network into the cross entropy loss, the loss is going to make a loss comparing the output and also the label. So the next thing that we would do is called a backward pass. So in the backward pass, the gradients of the loss with respect to the model parameters will be calculated, and then the model parameters will be updated. So the weights and biases will be updated. So we will iteratively update the weights and biases, and finally we will try to optimize the loss. So let's just try to implement the forward pass. Forward pass would be simple, and it has to be self and batch. So we'll give the batch later. So now self dot layers of batch, and this has to be returned. Now we need to define the loss function optimizer and things like that. So the loss function is going to be criterion equals to torch dot cross entropy torch dot nn dot cross entropy loss. So nn is already something that we have imported, so we can do nn dot cross entropy loss, and the optimizer will be, we'll need to import. So we'll import it in here. From torch dot optim import sgd. We have imported stochastic gradient descent, and optimizer equals to sgd. And before this, we'll need to initialize the model. LR model, logistic regression model, equals to logistic regression of. Now we'll need to define input shape, hidden shape, and output shape. Typically this can also be given in here. Input shape usually doesn't change, but hidden state is something that we would like to change around when we are optimizing. So this is a best practice when it comes to input shape, hidden shape, output shape. Maybe 11, 20, and 6. And 6. Okay, now we can do config dot input shape, config dot output shape, config dot hidden shape, and we can give in here the parameters in our dot parameters and a learning rate LR equals to, I'll set it up as LR. So we have to give a learning rate here as well. LR equals to, there's nothing specific about the learning rate that I've given, I've just randomly assigned it. So now everything is set up, we can actually start writing a training loop, because we did not run it. So one more thing that we can give in the config is the number of epochs. Epochs equals, let's just say 5 epochs. Now we'll write the training loop as for epoch in range config dot epochs for batch in train loader our LR model forward pass of batch of X. So this is our output, network output. Then we will do loss equals to the criterion that we defined of our output and our batch of Y. So this loss, we need to calculate the gradients of this loss with respect to the weights and biases. So the reason why we are doing this is we don't want the optimizer to have any previous gradients. So we only want to find the gradients for the loss that we have for the current batch. And then we are implementing the step by stating optimizer.step. So this is pretty much the training loop. So if I want to print out anything, I can do it here, or in every epoch. If I want to print out certain matrices or anything, I can do it in here. So for that I will write another function, define matrix of output comma the label. So the output is going to be a gradient enabled tensor, so we need to detach it, which means this now it will be a normal tensor. So previously our output was actually a part of a gradient calculation, so we want the output to be out of that gradient calculation loop, and then we can use it in here. So that's the reason why I'm calling detach. And once we are called output.detach, actually the outputs right now is just random numbers, so we need to convert them into logits, and then we need to convert them into valid predictions of the highest of the probability. So torch.argmax of torch.softmax comma this is what we would do. And what I've done was just I gave a softmax function, so which will convert everything into valid probability, and then the argmax function to get the label with the maximum probability, which is essentially our predictions. Threads comma label. I'll call it labels. and this both can actually now calculate any of the sort of functions. So for that I can call from sklearn dot metrics import accuracy score and recall score comma f1 score comma precision score. So all of these kind of parameters can actually be calculated now. And recall score of the same thing, accuracy score and recall score and f1 score, and precision score. Average equals to weighted, and here also average equals to weighted. Weighted. Okay, so I can call it accuracy equals to recall equals to f1 equals to precision equals to, and I can return all of the things: accuracy and precision, recall and f1 recall score, no recall. And so if you want to calculate the loss function or print out the losses, so you can print out the average loss per epoch. So what we can do is define something called losses, and for every epoch total loss is going to be 0, and after we calculate the loss function, total loss plus equals to loss dot item, and in the end what we can do is average loss equals to total loss divided by ln of train load. And you can choose to print average loss every time you do this thing, so it's gonna print the average loss. As you can see, there isn't much happening in here because we only have given like 5 epochs or so, and also it's because of the problem and the feature engineering, and a lot of the things has to be done for reducing the loss further. So this is just a mere introduction and some sort of a demonstration towards how we can actually implement logistic regression using Torch. So also one more thing that I can specify in here is like the metric function that I've written. So if you want to use the metric function and print out any of the metrics, what you can just we already specified this metric, and this metric is outputting accuracy, precision, recall, and F1 score. So you can either output and our batch of y, which is our label batch of y. This can be passed in, and this is going to print all of the metrics that we want to return. So this is totally customizable. And if you don't want that, or if you only want to print metrics in a after every epoch, then the only thing that you have to change is the output and the batch, because this time the output has to be all of the data points that you have passed in through one epoch, and the labels also has to be all of the data points corresponding to the outputs in one epoch. So that's it, and I hope you got a good introduction on how to build a logistic regression model and train it on PyTorch.